In this chapter, students learn how to identify and generate equivalent ratios and proportions. In previous lessons, students have learned how to write and create ratios. Students also learn that ratios are a multiplicative comparison. Equivalent ratios are described as being in the same ratio, or they have the same unit rate. For example, let's look at the ratio 1 to 2. Let's double the ratio to create an equivalent ratio of 2 to 4. Now let's triple the initial ratio to create 3 to 6. They are all equivalent ratios. While it is mathematically possible to create equivalent ratios for any given ratio, it doesn't always make sense to do so. Students will be given the opportunity to discuss situations where the real world may be different from a mathematical situation. For example, purchasing 3 apples for $1 is extendable to buying 6 apples for $2. However, the ratio of the number of times a baseball is hit to the total number of times at bat does not lend itself to extending. If a baseball player hits 4 out of 5 times at bat, it would be really difficult for them to maintain the same ratio after 50 times at bat, with an equivalent ratio of 40 out of 50. Another item to note is when to use a simplified ratio. Working with simplified ratios can be useful. However, it may also not make sense. For example, the ratio of 3 toys for every 4 children has a rate of 3/4 per every 1 child. There are 2 different perspectives on ratios discussed in this chapter. The first being a ratio as a composed unit. A composed unit is a batch that can be repeated or partitioned to create new pairs of numbers that are in the same ratio. For example, students look at creating multiple batches of orange juice in a lesson. The recipe of orange juice is made from 4 cans of water and 2 cans of orange juice. The batch can be repeated as seen here. The batch is repeated 3 times for an equivalent ratio of 12 cans of water to 6 cans of orange juice concentrate. The batch can also be partitioned or subdivided as seen here. This batch is made from 1/2 of a composed unit. Students will record their findings in a table as seen here. For example, a batch could be made from 3 groups. 3 groups of a ratio of 4 to 2 is 12 to 6. Or a batch could be made from 1/2 of a group. 1/2 of the ratio 4 to 2 is 2 to 1. Notice that the number of groups varies and the size of each group is fixed. The second perspective looks at ratios as a fixed number of parts where the size of the parts vary, or in other words, the number of groups is fixed and the size of each group varies. Let's use the orange juice example. The ratio is 4 cans of water to 2 cans of concentrate as seen here. Each part is 1 can. This next image shows the recipe tripled. The ratio is still 4 to 2, but each part is now 3 cans instead of 1 can, or the amount of each group has changed from 1 can to 3 cans. Both perspectives generate equivalent ratios. Students will start with sets of ratios that are easily solved by iterating or partitioning. Then, when students are familiar with making equivalent ratios, they will be given more difficult problems. Students will then move on to proportions. A proportion is an equation stating that 2 ratios are equivalent. Students will solve a proportion by finding one unknown in an entry table. In the chapter, students solve a frog jumping task where they need to find how far a human could jump if a human jumped like a frog. If a 3-inch frog jumped 60 inches, then how far would a 54-inch human jump? Students will work to find the missing piece using proportions. Students will use this knowledge in 7th grade when they begin to represent equivalent ratios with equations and graphs. In this chapter, students learn how to identify and generate equivalent ratios and proportions. Students begin with easy-to-manipulate ratios and use visuals and tables to represent their thinking. They will then move on to finding more efficient strategies to solve more complicated ratios and proportions.